All right, welcome back. Organic Chemistry 2341. We're going to continue on with Module 10, and then we're also going to get into Module 11. We're on our last two modules of the year. We have to finish up radicals, and then we're going to start talking about alcohols. And the most important thing about the alcohols chapter is that we're going to be doing some work with the Grignard reagent, and that's going to be a very interesting difference from some of the reagents we've used up to now. So let me go ahead and share my screen. And let me go ahead and move it over here. There we go. And I'm going to move my gallery view up over here. And I need to let somebody in. There we go. All right, we're letting people in now. Okay, so the last time we were here, we were talking about how there was a different selectivity between the reactions in fluorine, chlorine, bromine, and iodine. And what we learned from this slide is that the fluorine reaction is very exothermic. If we compare all the bonds broken and subtract all the energy from the bonds formed, we saw that fluorine was very exothermic. Chlorine was a little bit exothermic, bromine was barely exothermic, and iodine was endothermic, okay? And what we also saw is that in this case, the formation of the secondary chloro and bromide are more exothermic than the primary bromo and chloride, okay? And that is it's not a very big difference, but it's really close to the temperature at which we're running the reaction. This is a huge amount of energy given off. And so it's very exothermic and it'll heat itself up. And so it'll be able to go through either reaction mechanism because it's so exothermic. Okay, so let's talk about reactivity versus selectivity. Okay, so if you have a reaction that is really exothermic, that means it's very reactive. If it's more reactive, it's going to be less selective. Okay, so let's dig into that a little bit more right here. And so when we look at the difference between the fluorine and the iodine, the fluorine is very, very exothermic and makes very strong fluorine hydrogen bonds for the acid given off and the fluorine carbon bond. Okay, so, but if we look at the iodine, we have very weak bonds between iodine and hydrogen and carbon and hydrogen. Just empirically, they're weak bonds because it's a very long bond, right? Because iodine is very large, and so it's going to give a very long bond, and therefore it's empirically weaker than the short, strong fluorine hydrogen bond. And what we found is that it was actually endothermic, where it would take energy, dumping energy in to actually make it go. And it turns out also that the iodine radical is quite stable, and there's no driving force to make it abstract the hydrogen from the alkane to make that weak iodine hydrogen bond. So basically the iodine just does not work very well or at all. We have almost zero product from that system. Okay, so if we look at the difference between the fluorine and the chlorine in that's abstracting a primary or a secondary hydrogen, we see that the hydrogen abstraction of the primary hydrogen is slightly more exothermic in fluorine and chlorine, okay? Slightly more exothermic. However, the fact that they are not that big a difference, it is going to give us a little bit of secondary and a little bit of primary. The biggest difference in the bond dissociation energies is in the formation of the radicals. Chlorine is far less exothermic in both the formation of the chlorine hydrogen bond and the chlorine carbon bond, okay? That means that it is going to be able to wait around and take the one that has the slightly more exothermic route, and therefore it's going to enhance the number of secondary hydrogens it goes over versus the primary hydrogen. Even though there are 6 primary hydrogens and only 2 of the secondary hydrogens, it is less exothermic. It can wait around and do it. Now, when we look at the bromine radicals are far more stable and have slightly weaker bonds than the chlorine hydrogen bond, the fluorine hydrogen bond. And so even though it is a net exothermic reaction, the abstraction of the hydrogen by that bromine radical is endothermic. It takes energy, okay? And that makes the, but when we compare the primary to the secondary is slightly less endothermic. Okay, so even though the net reaction is exothermic, the actual abstraction to create that carbon radical is more energetically favored for the secondary abstraction because it is less endothermic. It took less energy to drive it to there. Now, once it forms that secondary radical, it then will react with the bromine quite readily. Okay, so do we start to see that the driving forces here are all about where we're going to get our energy out and where the bonds are storing that energy? The chlorine carbon bond and the fluorine carbon bond are very different in energy. We have much more energy given off during that carbon fluorine bond than in the chlorine or the bromine. Okay, so we can also explain this by the idea that with the Hammett principle. Remember the Hammett principle says that the transition state is exothermic when it resembles the starting materials, but the transition state is endothermic when it resembles the product. So if we're talking about that, it means that the hydrogen-carbon bond is shorter in an exothermic reaction because it's looking like the starting materials, and the carbon-hydrogen bond is longer in the endothermic because it means the bond is more than half broken and the new bond is more than a half formed. Okay, so what does that look like? In the case of fluorine here, we have it looking very much like the starting materials, okay? Meaning that if we have the hydrogen abstraction from the primary or the secondary, it actually just looks like the hydrocarbon and the fluorine starting to has a longer fluorine hydrogen bond, and therefore there's a less difference in energy between the transition state from the primary radical and the secondary radical because it looks more like the starting material, okay? So because of that, there's very little difference, and therefore you can get both of the pathways to happen in that first abstraction of hydrogen. Now, in the case of chlorine, it's still toward the beginning, but it's a little longer carbon-hydrogen bond and a little shorter hydrogen-chlorine bond. So this gives a slightly higher transition state for the primary, but there's still a small enough difference that we're going to get both of them. But we're starting to see this difference in the material, and we'll start to see that we can start getting a little more selectivity. More of it's going to form the secondary because it's slightly lower in energy, but we're still going to form a significant amount of primary. In bromine, it starts to get a little different. In bromine, we've actually almost broken the bond between the carbon and the hydrogen and almost formed the bond between the bromine. That means it's looking more like the products. As it's looking more like the products, it means it needs to form the more stable radical. The more stable radical is the secondary radical. So the energy difference between the secondary radical and the primary radical is getting much, much bigger. Okay, when that difference is bigger, we're going to get selectivity toward the secondary because we'll not have as many molecules able to get to this higher energy level. And we have most of them going through this lower energy level, forming the secondary. Okay. So this is why we have that selectivity in the bromine. It's all about where the bond making and breaking is during that transition state and whether or not you had to form a partial radical on your carbon center. If you're forming that partial radical because you have more of that bond broken, you're going to be trying to form the more stable radical at the lower activation energy. Okay. So what that means is that if you are very reactive, you're going to have low selectivity because the difference between the two transition states is going to be less. If you have low reactivity, you're going to have a higher selectivity because you're going to have a bigger difference in that transition state going from a primary or a secondary. Okay. Which means that bromine is much, much more selective at giving you that more stable radical, and you're going to get that in a specific location, unlike fluorine, which is going to give it the opposite product ratio. Okay, so let's talk about selectivity and reactivity. Okay, so statistically, we have 3 hydrogens here and 3 hydrogens here, which are equivalent because they're primary hydrogens. And then we have 2 hydrogens here. So basically we have a total of 8 hydrogens available to us, and 2 are secondary and 6 are primary. Okay, so of the 8 total hydrogens, we have 6 of them that are secondary, primary. So which means that in any reaction, if it wasn't selective, it should happen 75% of the time happen on the primary and 25% of the time on the secondary, just by statistics. So the fluorine is much, much closer to that statistical number than we see with the chlorine. And that's because it's much more reactive and doesn't care whether it's a primary, secondary, or tertiary formation of that radical. And therefore, it gives us the most statistical breakdown of the product ratio. Okay. Now, this leads us to an idea that maybe there is a reactivity ratio between the primary, the secondary, and the tertiary. Okay. So it turns out that each halogenation has a relative selectivity based on what type of radical it needs to form, whether it's a primary radical, secondary radical, or tertiary radical. In fluorine, if we call the primary 1, it's about 1.2 times more reactive as the secondary, and it's 1.4 times more reactive with the tertiary. Okay, so that means that there's really not that big a difference between them. It's 20% here and 40% here. Let's look at chlorine. Chlorine, if our primary is 1, the secondary is almost 4 times more likely to react, and the tertiary is 5 times more likely to react. Okay, that means that for every time you do this reaction, 4 out of 5 times it'll react with a secondary over the primary. Okay, now let's look at bromine. With bromine, because it's a lot less reactive, we end up getting a much bigger selectivity, 82 times that of the primary, and 1,600 times that of the tertiary. Okay, so we can use that numbers and the total number of reactions possible to predict our product ratio. So let's pull this up here, and we're going to do the chlorination and the bromination. So in this right here, in this example, we have 1, 2, 3 methyl groups. Those are all primaries. And we have a total of 9 primary hydrogens. And then we have 1 tertiary. And so we have 1 tertiary. So we have a possible total of 10 sites that can react. Okay. So if we look at that primary, we have a relative reactivity ratio of 1, and we have 9 hydrogens available to us, giving us a total of 9 for the reactivity ratio times the number of hydrogens we have. We have 1 tertiary, which has a reactivity ratio of 5.1. So we have 5.1 times that 1 hydrogen. And so that's going to give us the total number of the total rate of formation is 14.1, because we have this is equal to 9 and this is equal to 5.1, which means of those 9 reactions that are going to react with primaries, it's going to be 9 divided by the total number of reactions, which is 14.1, which gives us a 64% likely yield of that primary halogenation. Now, if we take this 5.1 divided by that 14.1 again, the sum of the total number of reactions here, we get 36%. And this is pretty close to what we see in actual synthesis. But now let's do it for bromine. So chlorine was a little bit selective. It had some of the tertiary, but most of it was the primary. Let's look at bromine. Bromine, a relative ratio of 1, so that's 1 times 9 hydrogens available to us. But the tertiary is 1,600 times faster. So we only have 1 hydrogen there, so 1,600 times 1. And then so the total number of reactions possible is 1,609. So if we divide 9 by 1,609, we get 0.6%. If we divide 1,600 by 1,609, we get 99.4%. And this is pretty close to the reaction ratio we see. it's going to be 99% the tertiary because of that higher reactivity ratio. Okay. So that brings us down to highly reactive, less selective, less reactive, more selective. Okay. And so we can actually predict it knowing these reactivity ratios. Okay. All right. So let's talk stereochemistry. Okay. In general, we really don't have that much stereochemistry associated with the radicals because it's like a carbocation. The radical abstraction can be done on the top or the bottom. So we're going to end up with a racemic mixture of a stereocenter. Okay, so that becomes now is something we have to know because there's no selectivity of that. We're going to get a mixture of the products. Okay. One of the cool things about halogenation, though, is that if you have a secondary carbon next to a quaternary carbon, you are going to get your bromination at that secondary carbon. It will not rearrange like a carbocation. Okay, so in the case of here, we have this substrate. We form the radical on this secondary because it's the most stable, and it's not going to move. It's not going to rearrange, which means we end up with our bromine primarily on here, 99% yield of our bromine on our secondary. Okay, and only 0.6% somewhere else. Okay, so, or it's actually 79. Yeah, sorry, this is a secondary, not a tertiary. But notice, because we're not forming a carbocation, we can't get a 1,2 methyl shift or a 1,2 hydride shift. Okay, if we were to go through the carbocation intermediate, for example, this acid catalyzed dehydration, where we end up with a carbocation, we're going to end up with a methyl shift. And if we end up with a methyl shift, that means we'll then have a bromine on a tertiary carbon and not on the original secondary carbon. In fact, we've rearranged our skeleton. So that's one advantage of using radical reactions over carbocation reactions, because they do not rearrange. Okay, so the last two things I want to talk about is benzylic and allylic bromination. Turns out that because benzylic bromination, that's where we have a bromine on an CH3 group outside a benzene ring. The benzene itself doesn't react with bromine or chlorine by itself. Okay, but that alpha carbon hydrogen does, and it reacts very quickly because of the stable radical it forms, because you can delocalize it around the ring, but it only reacts at the carbon that is adjacent to the benzene ring, and you get 100% yield on the system. However, when you do it with chlorine, you actually get a mixture of products because you're going to get partial reaction at that site because it's more reactive. Okay, so and the bromine is going to wait around for that most stable radical to form. The chlorine is more reactive and therefore is actually going to mess with the benzene ring. In the allylic system, that's where we have our double bond here. And when we form our radical, we get a resonance structure that gives us a nice stable radical here. Because it forms this stable radical very, very easily, because these are fairly easy to dissociate them, we end up seeing that we get a very high yield of the reaction because it's very easy to make this radical. And as long as you're symmetrical, you have very high selectivity at going only on that terminal primary site. And yeah, that's what I want to say there. Okay, so I said that sometimes in the allylics, if it was symmetrical, you have a one reaction and very high yields. However, there are a couple side reactions that you need to worry about if they are not as symmetrical, not just the allylic right here, where you have a possibility of putting extra halogens on somewhere. So one of the possible reactions you can do is you can form your bromine, your radical addition across your double bond, and then that's reversible. Actually, it can go back and forth, back and forth. But once you form this radical here, it can either react with bromine to give you a second bromination, or it can react with benzene. I'm sorry, it can react with HBr to give you hydrogenation at this site. So you have a possibility of getting mixtures of dibromo products. In fact, you're always going to get a little bit of the dibromo. And the best way to avoid that is making sure you have very little bromine in your solution at any one time. And that will encourage it to react with the HBr preferentially instead of the bromine. Okay. The other thing that really helps in the allylic bromination is using nonpolar solvents. The reason using nonpolar solvents will work is because you will not be able to just do that bromine addition across the double bond. It won't be able to stabilize that bromonium ion. So by doing your radical reaction in a nonpolar solvent, you're encouraging it to do the monobromination hydrogenation reaction instead of the a dibromination that we would see in the bromonium ion. In addition, in the bromonium ion, you would know that that was going to be anti-addition, where in the other, where you had hydrogen bromide add across there, you would not have a cis or anti in there because you'd have two hydrogens on the one carbon. All right, so that brings us to a new chemical that allows us to do very selective bromination because we're not going to use a significant amount of bromine in the solution at all. We're going to actually generate the bromide radical. So we're going to preferentially form a just a single bromine product. Okay, so that thing is called N-bromosuccinimide. So succinimide is this dicarboxylic acid right here with a nitrogen here. And we actually have a nice weak nitrogen bromine bond. Okay, so you can use heat or light to generate a small amount of that bromine radical, which is regioselective to react with the allylic hydrogen. Notice it doesn't add across the double bond like the bromine in the previous reaction. We only get bromine adding allylic, so one carbon over from the double bond, and it's very selective about doing this. And the whole point is we are not having bromine itself sit around there. We're just generating our we have very little bromine sitting around. Most of the radical is generated by the NBS. Okay. So one of the drawbacks is that NBS is not very soluble in nonpolar solvents. And so it reacts quickly with HBr to produce bromine at low concentrations. And then the bromine actually will perpetuate the reaction by generating more bromine radical. Okay. So before we talked about this in the alkenes section, I'm just going to review it quickly, is that we can use peroxides to generate our addition of HBr across double bonds. But when we do it, it goes anti-Markovnikov because in the intermediate, you're trying to form the most stable radical. And so the radical is always going to be on the more substituted side. So you're always going to get halogenation at the least substituted. Again, we talked about this in chapter 8. So what that looks like is that we'll always get that reaction happening. Okay, now, unlike HBr, chlorine actually won't do this reaction because the radical formed is actually higher in energy than the starting material, and therefore it makes that taking of the hydrogen away from the HCl endothermic. So this is only successful with HBr. Notice I only used HBr in the last chapter with that radical initiator because it only works with bromine. Bromine's the only one that's going to form an exothermic bond. In the case of iodine or chlorine, it actually forms an endothermic bond, and therefore the reaction does not progress. Okay. So, and I think this is my last slide. Yeah. I'm going to do this one instead. So if we use the radical mechanism, we end up getting an anti-Markovnikov's product when we add that HBr on there, because the intermediate we're forming is going to be the more stable radical, which is the more substituted radical, because bromine attacks first. Okay, so we're going to form the more stable radical. Now, in the ionic mechanism, where we have the alkene acting as the nucleophile, and we transfer the hydrogen first, we're going to form the most stable carbocation. Okay, so we've transferred the hydrogen first in the Markovnikov's addition, and that gives us our carbocation on our most stable carbon, which gives us our bromine on our most substituted carbon. So we can choose whether to have our bromine on our least substituted side of our alkene or our more substituted side of our alkene by choosing the right reaction. Ionic for Markovnikov's addition, radical for anti-Markovnikov's addition. All right, questions on radicals? I'm not muted. Okay, great. Okay, so now we're going to switch gears and get into our last chapter, which is alcohols. Okay, so what we're going to do with alcohols is we're going to look at, the first thing we're going to look at is their properties. Okay, now remember, go back and look at how to name these. Don't forget about that. That's also going to be, come on. There we go. So alcohols are, of course, one of those functional groups we like. And when we talked about them with acids and bases, yeah, it is a lot. And we're trying to get, through the end of the semester, though. All right. So alcohols, we know, are weak acids, but they're also weak bases. Now, that's actually to our advantage, because if you protonate an alcohol, it becomes a strong acid. Okay. And if you deprotonate your alcohol, it becomes a strong base. Okay, so your alcohol can act as a Lewis acid by being able to transfer that proton, a Bronsted-Lowry acid by transferring the proton, or it can act as a Lewis base by using that lone pair to abstract a hydrogen from something else. Okay, so when we call a molecule that can be kind of both things, it's called amphoteric. Amphoteric. It can be used as an acid or a base. Okay. So this is what we're going to learn in this module here. We're going to learn about a nucleophilic addition reaction, which is an SN1 reaction to produce alcohols. And we're going to talk about the Grignard reagents and that acetylide ion we talked about in 2 chapters ago. Okay. We're also going to talk about how to reduce down carbonyls to produce alcohols, specifically with a hydride transfer agent. Okay. Then we're going to be able to oxidize alcohols to produce carbonyl compounds. So we're going to talk about oxidation and reduction. And then we're going to do ring opening with epoxies and conversion of alcohols to better leaving groups. OH is a bad leaving group, so sometimes you want to convert it to something else and make it into a better leaving group. Okay, so let's start with our nucleophilic substitution reaction and the Grignard reagent. Okay, so we introduced a very strong base 2 chapters ago called butyl lithium. Okay, butyl lithium is basically a lithium reagent with a polar covalent bond between carbon and a lithium. In that case, lithium was less electrophilic than carbon, therefore the negative charge, or the partial negative charge, resides on carbon. Okay, so we're going to take advantage of that partially negative charge on carbon to do some really cool chemistry and use that carbon as a nucleophile. Okay, so, but we can do it with other reagents other than lithium. There's a reagent we can use with magnesium that creates that same type of polar covalent bond where the negative charge resides on carbon. And we call these Grignard reagents. And they're fairly easy to make by taking elemental magnesium, and then it's going to give up 2 electrons to insert itself in between that carbon bromine bond. And when it does that, the partially positive charge is carried by the magnesium because it's the less electronegative atom, and the negative charge is going to be carried by the carbon. Notice this can be done with aliphatics, it can be done with aromatics, and it can be done with vinyl hydrogens, okay? As long as there was a bromine on any one of those, magnesium will insert itself, and so we can use any of these reagents as a nucleophile, okay? So that's a little bit different than we've done before. So that's why these magnesium reagents, which are also called Grignard reagents, and the organolithium reagents are really useful as nucleophiles. Okay. So the way we synthesize this is we usually have to use it in ether because the ether is going to support the complex made because of its dipole-dipole interactions and it acting as a Lewis base. The electrons from the ether are going to help support it. And we have to be able to get that magnesium in. So the first thing we're going to do there is we're actually going to transfer one electron from the magnesium to the halogen and creating a carbon radical and a magnesium radical. And because they're really close together, they're going to form a new sigma bond. So technically, magnesium has just given up 2 of its electrons to make 2 sigma bonds. Both of those bonds are polar covalent bonds. Okay. With butyllithium, it's similar where we take a lithium metal and it does insert itself in there, but it takes 2 equivalents because you end up with 1 lithium being on the carbon and 1 lithium counterbalancing the halogen. Okay. So with magnesium, you just need 1 equivalent because it's going to insert itself in the bond. With lithium, you'll need 2 equivalents because you'll need to make the lithium halide. Okay, so I told you this is a polar covalent bond. Okay, so if we were to think about a resonance structure for that, it would be fluctuating between that polar covalent bond and that contact ion pair, where they are the negatively charged carbon is right next to that positively charged magnesium. Okay, now in the case of magnesium, it has about 30% ionic character. So it spends 30% of its time in this portion here, and it spends 70% of its time in that covalent bond form. With the lithium here, lithium is a little less electronegative than magnesium, and therefore it's a slightly higher ionic character. It spends more of its time than magnesium as that close contact ion pair. And so that makes it nice to have, you know, 40% of your time, you're going to have this nice nucleophile to do a reaction. Okay. Now, what is that shape of that carbon anion we have? Well, carbanions are going to be 2 electrons in an unhybridized p orbital. Okay. So in theory, carbocation is planar because it's sp2 hybridized. But because the carbanion is sp2 hybridized, but it has 2 electrons in its p orbital, it actually pushes the groups out and it's sort of pyramidal. Okay, so we're looking at this is not very sterically hindered and can act as a very good nucleophile and as a very strong base. Okay, so how can we use this as a nucleophile? Well, we can do it with anything where we can have a attack by an anion is going to be good. So if we look at an alkene really doesn't really have a polar bond and it has electrons in a pi. So it's not going to be specifically reactive to these nucleophiles. However, if we look at a carbonyl compound, because that's a polar covalent bond, we have a partially positive side on our carbon and a partially negative side on our oxygen. That means it's susceptible to attack by nucleophiles on that carbon. Okay. So how does that work? Well, when we have the addition of a Grignard reagent to a carbonyl compound, we have attack by the partially positive carbon to that partially negative carbon, attacking the partially positive carbon, giving us a new carbon-carbon bond right here. And then, of course, those electrons kick up and reside on the oxygen, and therefore the magnesium counterbalances that charge on that oxygen. Okay, so right here we have a deprotonated alcohol with a magnesium complex. Okay, now that is going to stay that way until you break up that magnesium complex and protonate that alcohol with acid. Okay, so generally we say either dilute HCl or hydronium ion and water, but you do need acid to protonate that alcohol and break off that magnesium. Okay, so that attack by a Grignard on a carbonyl is a fairly universal reaction, but you can choose what substrate you use, and that substrate you use can determine what products you get. Okay, so for example, let's say you wanted a primary alcohol. Okay, that means you have to attack a carbonyl that already has 2 hydrogens on it. Okay, the carbonyl that has 2 hydrogens on it is formaldehyde. Okay, so if we take our Grignard reagent, it can be any Grignard reagent, and our formaldehyde that already has those 2 hydrogens on it, the first thing we're going to do is we're going to create that new carbon-carbon bond at that carbonyl carbon, and then we're going to decompose that magnesium salt to give us a primary alcohol. Okay, so if we want a primary alcohol, we need to attack a formaldehyde with a Grignard reagent. Notice also that the alcohol we formed has 1 more carbon on it than the Grignard reagent. So if you wanted heptanol, you would have to attack with hexane and then attack the formaldehyde with that hexane magnesium bromide to get a total of 7 carbons and your primary alcohol. Okay, so let's say you didn't want a primary alcohol, you wanted a secondary alcohol. Well, that means you can use any other aldehyde than formaldehyde. Okay, so as long as you have 1 hydrogen on that carbonyl, so it's an aldehyde, you will end up with a secondary alcohol. Okay, and notice here, by choosing your species, choosing your aldehyde and your Grignard reagent, you can make these symmetrical or unsymmetrical by just choosing which aldehyde to start with and which Grignard reagent to start with. And you still have your hydrogen here, so you have your secondary alcohol after workup with acid. So if you have a ketone, you will always generate a tertiary alcohol because you already have 2 R groups on there for the ketone. You're attacking it with a new R group as the nucleophile, generating a tertiary alcohol. Okay, so what that means is that by selecting which groups you have on your ketone and what group you're attacking there, you can make a wide variety of tertiary alcohols using that system. The other cool thing is you can also attack carbon dioxide. Think of carbon dioxide as, you know, a carbonyl, but it has 1 on both sides. It still can attack that middle carbon. When it does, you end up forming a carboxylic acid, okay? Because there's already 2 oxygens on that carbon. You're not going to break one off. You're just going to form a new bond that would give you our carboxylic acid. So see the utility of using a Grignard reagent to make a wide variety of products here. All you need is a Grignard and a carbonyl, and you can make alcohols and carboxylic acids. All right, questions? All right, let's move on to the generalized mechanism. The generalized mechanism is that we have a nucleophile. It's going to use those electrons from the nucleophile to attack the partially positive carbon. Then the double bond between the carbon and the oxygen gets flipped up and stabilized on the oxygen until you protonate it with acid. Okay, so I said you can make a wide variety of things as long as you have a carbonyl. Okay, well, esters have carbonyls too, right? It has a carbonyl and an OR and some kind of alcohol attached to it. Okay, the problem with this is that when you do your first attack, you make this substituted product here, where you have 4 things bonded to carbon. Okay. But notice that we don't remove hydrogen or carbon during this reaction because they're very bad leaving groups. Okay. Our Grignard reagent is a very strong base. Okay. So that it's in a very basic solution. What can happen is that the OR can leave as an anion. It's a good leaving group. And that's what will happen because it'll try to regenerate the lone pair from the oxygen will get here to regenerate the carbonyl compound. And you'll end up with a ketone. Okay. Now, problem is you now have a carbonyl compound. So any Grignard laying around is going to react with that ketone to generate a Brianna, do you have a question? Your mute, your mic's on.
Sorry, sir.
Okay. Okay, so now that you've regenerated that carbonyl compound because the OR, the alkoxide as a leaving group left, you can then attack it with another equivalent of the Grignard reagent to make a tertiary alcohol. But note, you will have to use just 2 equivalents of the same Grignard reagent. It's very difficult to stop in the middle. You're going to have some of it go. So the idea is you use 2 equivalents of the same Grignard reagent, and you end up with 2 equivalents of that same group on your tertiary alcohol. Okay. So when you have that ketone, you can have all 3 R groups be different when you attack it. When you use a Grignard reagent with an ester, you're going to get 2 of the same units and whatever was on that ester, whatever the R group on the ester was. Okay, questions on Grignard reagents. Okay. So they're really, really useful for making these alcohol sets. Okay, so the basic mechanism is we get attacked by our nucleophile first. It gives us our tetrahedral center. But we have an alkoxide as a decent leaving group. The alkoxide leaves as a decent leaving group, regenerating our carbonyl compound, which can then be attacked by another nucleophile, which will give us our tertiary, our tertiary salt, which then we hydrolyze with acid to generate our alcohol. Okay. So, because these organolithium reagents and organomagnesium reagents or Grignard reagents are very strong bases, they react with anything with an acidic proton, which means you have to be very careful about what you use as a solvent for your system and whether or not there is something with a proton that can be transferred here. So the idea is that we have the anion, this carbon anion. Remember, all the pKa's for these, are above, acetylene is 25, alkenes are 44, and alkanes are 50. So, we're going to have this anion here is going to be very, very basic. It's a very poor acid, so it's a very strong base. And so in the presence of water, it's going to basically transfer a proton and quench the reaction. Okay. So you have to be very careful about moisture, alcohols, or anything that can be attacked by a strong nucleophile. Okay. So if we get the desired reaction, we'll actually form our, in this case, a secondary alcohol by adding an aldehyde. Okay. So this can actually be used to our advantage if we're trying to probe the mechanism of some kind of system. For example, let's say we wanted to mark our reagent with deuterium. Remember, when we did proton NMR, only hydrogen 1 was NMR active. Hydrogen 2 or deuterium was NMR inactive. So you can actually take an NMR of your material before and then deuterate the material and take it again, and you'll know exactly which part of the molecule reacted by seeing whether that deuterium is missing from the system or whether that deuterium has been taken off and has been replaced by a hydrogen. So it could be very useful to use that for that. But that would be the only reason you would want to quench a Grignard with water. or in this case, heavy water. All right, questions on Grignards? Basically, the Grignards and butyllithiums are making very strong bases and making very good nucleophiles. All right, so let's move on to another good nucleophile. And we talked about this a little bit with the in the acetylene chapter about acetylene can be deprotonated by strong bases. Well, it turns out the Grignard reagent or the butyllithium reagents are much stronger bases than sodium amide, which means that they also react with those hydrogens of acetylene to create a reagent. So if you had a Grignard reagent of ethane, the ethane proton is much, much less acidic than the acetylene proton. So it's going to abstract that hydrogen and put the Grignard onto the acetylene and generate our weaker acid here. Notice, I mean, it's not a very strong acid, but this is a much weaker acid. And so it's going to exchange, giving you the acetylene now as your nucleophile. Butyllithium does the same because the alkane has, again, a very high pKa. The acetylene doesn't have a very high pKa, but it's lower than the butane we just made. So it goes and makes our carbon anion of our acetylene. Or you can also do it with the sodium amide to generate this plus ammonia. Okay, it still all goes. Now, with the sodium amide, that reaction tends to have to be done in liquid ammonia, which is very difficult because liquid ammonia is like minus 37 degrees. So the advantage of using the Grignard or the butyllithium reagent to generate your acetylene ion is it can be done at room temperature in a good solvent like THF, tetrahydrofuran. So it could be an advantage to work on a number of different substrates for that. Then, of course, once you have your acetylene as your nucleophile, it's going to attack your carbonyl compound, generating your salt of your alcohol that you have to protonate with acid to generate either a secondary or tertiary alcohol, or if you have formaldehyde, it'll even generate a primary alcohol, and your alkyne is intact. Okay, so we can actually create some really cool structures like our acetylene is going to stay intact, and then if you attacked it with formaldehyde, you'd end up with a primary terminal alcohol. If you added with a different aldehyde, you'd have that, and if you added with a ketone, you'd have a tri-substituted tertiary alcohol. But the alkene stays intact. So that's a good way to incorporate an alkene, the alkyne stays intact, and that's a good way to incorporate the alkyne into the middle of a chain. All right. Questions on using these metal reagents as nucleophiles. Okay, so this is one of those things you're going to want to write down on your reaction table that I'm going to send out that assignment today. And it's going to be, acetylene with a Grignard creates what? And so we're going to see that when we want these triple bonds in our middle of our structure with an alcohol, we probably want to attack one using the acetylide ion in whatever form we have. If we can remember using these Grignard reagents, we can make primary, secondary, or tertiary alcohols, and we can make them symmetrical or non-symmetrical. So that's one of the very useful ways of using these reagents. Okay, so now we're going to talk about making alcohols with reducing agents. Okay, so by reduction. Okay, so in theory, we can do it with catalytic hydrogen. However, it would also reduce down any other carbon-carbon double bonds or carbon-carbon triple bonds. So we want to use something that's more selective just for the carbonyl. And with those, we have these lithium aluminum hydride and sodium borohydride. But let's remind ourselves what oxidation state was. We've already done this before. But our oxidation state, remember, is you get -1 point for each hydrogen, you get +1 point for each bond to oxygen, and 0 for each bond to carbon, which means our alkanes are our most reduced. Alcohols are the first step up because it's 1 bond to oxygen. Ketones and aldehydes are the next step up because 2 bonds to oxygen. Carboxylic acid is next up because 3 bonds to oxygen. And then, of course, CO2 is 4 bonds to oxygen, our highest oxidized carbon. Okay. So what we're going to be trying to do is go in the opposite direction. Instead of oxidizing things to give us more carbon-oxygen bonds, we're going to try to get rid of the carbon-oxygen bonds. And the specific reactions we're going to talk about is reducing down carbonyls to form alcohols. Okay. So we use these 2 reagents specifically, sodium borohydride and lithium aluminum hydride, because they are very selective to reducing down just the carbonyl. Okay. Lithium aluminum hydride is more reactive than sodium borohydride. In fact, it spontaneously reacts with water very violently to generate hydrogen and usually a little bit of fire. So we have to be careful when we do it. The sodium borohydride is actually usually run in an alcohol, sometimes water, so it's less reactive toward that and does not readily react with water. So notice that the major product given off here is 4 equivalents of hydrogen gas. So that's important that we try not to do that. Okay. So let's talk about what's happening here. Okay. So the key thing in lithium aluminum hydride, actually, let me show you something here, is that we have aluminum with 4 bonds to hydrogen and the net negative charge. And then the lithium is a net positive charge here. Okay. And what we're going to do is we're actually going to use both electrons from this aluminum hydrogen bond are going to be used to make a new sigma bond onto our carbonyl compound. Okay, so that's why it's a hydride. Proton is with a positive charge. A hydrogen elemental is with 1 electron. A hydride is hydrogen with 2 electrons and a negative charge. Okay, so because we have a negative charge on this hydrogen, we can now attack the partially positive carbon of the carbonyl selectively. So in the case of lithium aluminum hydride, right here, we take lithium aluminum hydride in some kind of non-aqueous solvent. And at the end of the reaction, we actually quench the reaction with water to protonate our alcohol. Okay. And so what we're going to do is we're going to add a hydrogen to the carbon here to give us our reduction from +2, because it has 2 bonds to oxygen, to only 1 bond to oxygen and 1 bond to hydrogen. So we get a -1 for that. We get a +1 for that. So our net oxidation state is now 0. Okay. So when we add our hydrogen to that carbonyl hydrogen, we get a secondary alcohol. Okay. If we do it to an aldehyde, our oxidation state is actually higher because we have a single hydrogen here at +1 and -1, and we have +2, so our oxidation state is only +1, which means when we reduce it, we now have 2 hydrogens on there, and our oxidation state drops to -1. Now, when we do it with esters, we're actually going to reduce off the OR group, and we're going to end up with our alcohol, and we're going to end up with a primary alcohol. Notice we got a secondary alcohol here, a tertiary alcohol here. I'm sorry, a primary alcohol here and a primary alcohol here. So we're going to add 1 equivalent of the hydride across here first, and then we're going to use the, it's going to lose the alkoxide and then reform the carbonyl, and then we're going to reduce it down 1 more time. Okay. And in the case of lithium aluminum hydride, we can even reduce down carboxylic acids. And again, it's going to reduce off the OH, and then it's going to reduce down the carbonyl and give us our primary alcohol. So notice, if we have anything other than a ketone, we're going to make a primary alcohol with an aldehyde, ester, or carboxylic acid using lithium aluminum hydride. Okay, so that being said, let's talk about sodium borohydride. Sodium borohydride is less reactive. Remember, it reacts less violently with water. And so we actually run these reactions in methanol, because the methanol is going to end up protonating our alcohol. If we do a ketone, sodium borohydride will add 2 hydrogens across the carbonyl of that ketone and give us a secondary alcohol, just like the lithium aluminum hydride. But if we use an aldehyde, it'll give us a primary alcohol because it'll reduce down this carbonyl, giving us a primary. However, sodium borohydride is not reactive enough to reduce down esters or carboxylic acids. Okay, so why is that important? Well, we now have selectivity. Okay, if you have a ketone and a carboxylic acid or a carboxylic acid ester in your compound, and you only want to reduce down the carboxylic, the ketone, you can selectively choose sodium borohydride to only reduce down the ketone and leave the aldehyde alone. Okay. Now, if you want to do it the other way around, you want to reduce down the ester, we actually have a trick for that. And we'll get to that toward the end of the chapter. Okay, so again, the reason we use these hydride reagents is they are very selective right here. They only attack carbonyls because we're transferring that hydrogen minus to attack the carbon, the partially positive carbon, the carbonyl. Okay, now we can use a catalytic hydrogenation to reduce down the carbonyl in the case of the catalysts of palladium, platinum, and nickel, but it's also going to reduce down any other double bond we have in our system or triple bond. Okay. Now, we can actually selectively reduce down just the alkene if we use one equivalent hydrogen and a weaker catalyst, palladium on carbon. It's not going to attack the carbonyl, but it does attack the alkene. So now we have, again, selectivity of using that. And if we have one equivalent of our hydrogen, it's going to only react with the double bond. Okay. So, but the hydride reagents, the sodium borohydride and the lithium aluminum hydride, do not reduce down the alkene. They only reduce down the carbonyl compounds right here. So again, this is one of those important things we're going to learn in our reaction table, is that selectivity of reagent is going to give us a better way to make a certain product, the exact product we want every time. All right, so what's the mechanism? So the first step in the mechanism is that we have the transfer of the hydrogen and both of its electrons to the carbonyl carbon, giving us a negative charge on the oxygen. The oxygen there is then going to act as a base and pull a proton off the alcohol in the solvent, giving us our primary alcohol and our alkoxide here. This alkoxide then actually helps stabilize the reagent here. Okay. Now, notice that when we lose one of these hydrogens, we now have BH3, which is a neutral molecule. The alkoxide actually attacks that neutral molecule to generate a new salt. Now it has 3 more hydrogens that it can transfer. And so it can react 3 more times to transfer all 3 of those hydrogens. And at the end of the reaction, we now have the tetra alcohol salt of the boron, and it's counterbalanced by the sodium ion. Okay, so that's a good thing to know, is that we only need to use, for every 1 equivalent of sodium borohydride or lithium aluminum hydride, we can use 4 equivalents of the carbonyl containing compound, because it'll transfer all 4 of those hydrogens off the boron. Okay. Lithium aluminum hydride is very similar in the fact that it's going to transfer that hydride, okay? But in the case of the lithium aluminum hydride, it actually, the aluminum complex forms between the alcohol you just formed and the aluminum itself, okay? And it will continue to do this. In the case of lithium aluminum hydride, we must use acid at the end to break up that aluminum oxygen bond to give us our aluminum as a salt and our free alcohol. Sodium borohydride gave us the alcohol from the solvent. The lithium aluminum hydride is not in alcohol and therefore forms this complex, having transferred all 4 of its hydrides off, giving us our aluminum salt that then has to be decomposed with acid at the end. Questions on the mechanism of these hydride reagents? The reason they're selective is hydrogen has the negative charge, the carbonyl has that partially positive charge, and we use that to our advantage to be very selective about attacking just the carbonyl carbon. Okay, so with esters, it's a little more complicated because what's going to happen is we're going to get our first addition of our hydrogen on the ester, and we're going to end up with this tetrahedral intermediate. But because we have the negative charge on oxygen, it wants to reform the carbonyl by kicking in a good leaving group, in this case, the alkoxide. Okay, so our lithium aluminum hydride is a stronger base, and so we can actually have that aluminum, that OH-OR come off, and then regenerate our carbonyl. If we regenerate our carbonyl, that means we're going to be able to attack with another nucleophile, and then we're going to end up with that alkoxide gone and 2 nucleophiles on there. That looks very similar to that mechanism we had with the 2 equivalents of Grignard when we attacked the ester. Okay, so what does it really look like with an ester itself? We're going to form this aluminum salt here first. Then this is going to kick in. We're going to transfer the alkoxide to the aluminum. Okay, so the aluminum is going to counterbalance that charge with our single hydride transfer and regenerating our carbonyl. Now, another hydrogen from that aluminum alkoxide compound can transfer over and reduce our carbonyl again, giving us our tetrahedral intermediate, which after we work it up with acid, we generate our alcohol, the alcohol that was the part of the ester, and aluminum and lithium salts. Okay, so do we see why in the ester, we end up with getting 2 attacks by nucleophiles? And in the ketones and aldehydes, we don't. Carbon anion and the hydrogen anion are bad leaving groups, but the oxygen anion is not as bad a leaving group and therefore is displaced, regenerating the carbonyl, which makes it susceptible to the second attack by nucleophile. All right. So with carboxylic acids, it's a little different, but kind of the same. What we're going to do is we're going to go ahead and transfer a hydrogen to our acid, our carboxylic acid proton, okay? And that's going to generate 1 equivalent of hydrogen and a lithium salt, okay? Now that we have that lithium salt, we've taken away any acidic protons with our first hydride. We are going to then attack our carbonyl with another equivalent of hydride to give us our aluminum lithium salt. Notice the lithium is what the lithium salt of the carboxylic acid is the first thing to form. And then we have our aluminum hydride salt with our alcohol here. Okay, so now that gives us a way to have oxygen leave. Oxygen negative by itself is not itself a very good leaving group, but when it's attached to the aluminum, it makes it a decent leaving group because the aluminum oxygen bond is very strong. So we're going to kick in the electrons from the oxygen that's bound to the lithium. Let me use that. Right here, we're going to kick those in and then kick that out to give us a negatively charged oxygen bonded to aluminum. That regenerates our carbonyl. So then once we have our carbonyl regenerated, we can then react it with another equivalent of the lithium aluminum hydride to give us our salt of our alcohol. And then after acidic workup, we end up with our free alcohol. Okay. Questions on reductions. Sodium borohydride only reduces aldehydes and ketones. It is usually done in an alcoholic solvent like methanol or water, methanol or ethanol. Lithium aluminum hydride is more reactive and will reduce aldehydes, ketones, esters, and carboxylic acids. It has to be done in the absence of acidic protons. The only one that can use the acidic proton is the carboxylic acid because you have very little, but you use up one equivalent of your aluminum hydride just making that first salt. Okay, so knowing that you can only do 2 things with the sodium borohydride and 4 things with the lithium aluminum hydride is important. All right, so let's go ahead and do some chemistry on alcohols. Okay, we're going to oxidize alcohols to make them something else. So we had carbonyl compounds and we turned them into alcohols by either using a Grignard reagent or a Hydride reagent, right? So now we're going to go the other way. Okay. So in the case of oxidation, what we're going to do is we're going to create a new carbon-oxygen bond in the system, or we're going to increase the number of carbon-oxygen bonds in the system. And the most common reagent we use for this is what we call the chromium or chromic acid. Okay. In the case of the chromic acid, we have, it's actually, CrO3, and then plus H2O generates chromic acid. Okay. Now, if we protonate that chromic acid, it makes it very susceptible to being attacked by the alcohol, the oxygen of our alcohol. Why? The chromium is a Lewis acid. The alcohol is a Lewis base. So the lone pair on the alcohol is going to act as a Lewis base and bind to the chromium. Okay, that's going to give us our initial complex here. Okay, notice that all of these so far are reversible steps. Okay, then what we're going to do is we're going to transfer our proton off of our oxygen onto one of these OHs on the chromium, making it a pretty decent leaving group. Okay, so now we can actually have this water leave this, those electrons kick in, and we end up with a chromate ester. Okay, so we've put our alcohol attached to our chromium, and our chromium is stable at this. But we're not done. We wanted to oxidize our carbon. So to oxidize our carbon, we need to have something act as a base and deprotonate the carbon attached to the oxygen. So in this case here, we have the solution in water. It's going to pull that proton off, kicking electrons in to make our carbonyl, which kicks our electrons out to generate our chromium species here. That chromium species then can be regenerated as chromic acid by adding water. Now notice in this step, we stopped at the aldehyde here. Okay, well, that aldehyde still has a proton on the carbon that was the alcohol, and it can be oxidized further to the carboxylic acid. Okay. So because our aldehyde here can act as a Lewis acid as well, we can then have water come in and act as a Lewis base, generating this hydrate or this geminal diol, 2 alcohols on the same carbon. That geminal alcohol then reacts with chromic acid again to form the chromate ester, and then it can transfer that last proton off to generate our carboxylic acid and a chromium salt. Okay, so when we use chromic acid in water, it will never stop at the aldehyde. It always decomposes to the carboxylic acid. So you have to be careful when you're using aldehydes because they are going to reduce down to the carboxylic acid. However, if you have a ketone it only has one hydrogen to transfer. So it only will oxidize down, I'm sorry, if you have a secondary alcohol, it only has one hydrogen to transfer and will always oxidize down to ketones, and ketones are stable to chromic acid. Okay. So RH goes to carboxylic acids. I'm sorry. Primary alcohols go to carboxylic acids. And secondary alcohols go to ketones. Okay. And then, of course, that, tertiary alcohols cannot be oxidized. The tertiary alcohol cannot be oxidized because there's no proton to be removed by the base, and therefore you cannot oxidize them. You cannot make a tertiary alcohol oxidized to anything else. So primary alcohols make carboxylic acids, secondary alcohols make ketones, and tertiary alcohols don't react. Okay. Questions on chromic acid and chromic acid oxidation? Okay, we got about 9 minutes left. So I'm going to introduce a way to stop at the aldehyde. Okay, chromic acid is too strong. It's going to, and it's using water. That water in that reaction will react with that aldehyde to create a hydrate, which is then susceptible to oxidation by chromic acid. So the key to stopping at the aldehyde is remove water, okay? But chromic acid is not soluble in solvents without water. So if we make a salt of the chromic acid using pyridine and HCl, it becomes an organic solvent, an organic soluble material, which means we can use a solvent that itself will not oxidize. In this case, we're using dichloromethane right here. Dichloromethane is an aprotic solvent. It has no hydrogens. If it has hydrogens or water in it, it will oxidize it to the carboxylic acid. So we have to have an aprotic solvent that is not easily oxidized. Okay. So how do we make our reagent first? Our reagent, we take pyridine right here, and then we take chromium oxide, not chromic acid, chromium oxide, and HCl, and it creates this salt called pyridinium chlorochromate, or PCC. So PCC is typically used in this solvent here. So you'll see PCC and methylene chloride or dichloromethane. And when you see that in there, you know that your primary alcohol is going to stop at your aldehyde because it's in the absence of water. Okay, so what do we learn in our oxidation? We can take our primary alcohol to a carboxylic acid with chromic acid. We can take a secondary alcohol to a ketone with chromic acid, and tertiary alcohols don't react at all. We also learned that using PCC, we can stop at the aldehyde. Okay. Now, PCC will also oxidize secondary alcohols to ketones. So that reaction is still available to us, but PCC is generally used to make just the aldehyde from our primary alcohols. All right, questions on that? Okay, so wow, we've learned so much. We've been able to use nucleophilic attack to make primary, secondary, and tertiary alcohols with Grignard reagents and lithium reagents. We've been able to make primary alcohols from aldehydes and ketones by using hydride transfer agents. And we've been able to take alcohols and turn them back into ketones and aldehydes by using oxidizing agents. And again, selectivity of reagent is the most important part about those things. Okay, so the next thing I want to talk about is forming alcohols by opening up a ring. Okay, now, when we talked about our nucleophilic attacks right here, we said that if we had a 3-membered ring, it was an ether. Ethers tend not to react with anything except that the 3-membered ring is so strained that it'll open up to nucleophilic attack. Okay, so when we have that system, we have an easy attack where it's going to attack one side, and it's going to attack at the more substituted side, and we'll talk about that in a minute, to generate our ring open material, and then by protonating, we end up with our alcohol. And we can use almost any nucleophile for this to generate a bunch of different things. Okay. Now, let's talk about why the epoxy or oxirane is the only ether to react. Okay. Oxirane starts out at a much higher potential energy because of the ring strain. Okay, so that when it's attacked by its nucleophile, it actually ends up being an exothermic reaction because it eliminates the ring strain and the reaction goes forward. Okay. However, ethers, when they're attacked by a nucleophile, would have to form an alkoxide and a new material, and those tend to actually be endothermic reactions. There's more stored energy in those alkoxide and that new material. Therefore, the reaction does not go forward. Okay, so the only thing that makes this ether react is ring strain. Okay, so it is a very, very useful reagent because we can make a wide variety of substrates from this. If we attack it with hydroxide, we get a 1,2 diol. Okay, so and you can have R groups here too, and you're going to end up with your R group here. So it can make any variety of 1,2 diol, carbon 1, carbon 2. Okay. So you can also make ethers with it, straight chain ethers with an alcohol at the end. Notice the nucleophile always attacks on the 2 carbon. Your alcohol is typically on your 1 carbon, unless you end up naming it for something else. You can attack it with sulfur. You can attack it with a Grignard reagent. Now, it will not be it will not be protonated until you add acid. Notice all of these add acid at the end. You can even reduce it down with lithium hydride to add across that oxygen carbon bond and give you a hydrogen there. So you can get your primary alcohol. And then again, cyanide can be used as a good nucleophile, and you would end up with this cyanoalcohol. But this no longer is the 1 position because you're naming it for the nitrile at the end. All right, questions on ring opening and the utility of these oxiranes. Okay, I got 3 minutes left. All right, so there's 2 ways to ring open this, okay? We can do it under basic conditions with a strong nucleophile or under acidic conditions. Under acidic conditions, we're trying to help the ring open a little bit before it forms. So in the case of nucleophiles, if it's a strong nucleophile under basic conditions, it's going to attack the least substituted carbon because of sterics, okay? Even though it's slightly longer bond here, it's still going to be a steric situation. Remember, this is a tertiary center. We don't attack tertiary centers with nucleophiles very often. So we're going to attack this primary center, and that'll give us our alcohol on our more substituted side. Okay. Okay. Under acidic conditions, what we're going to do is we're going to protonate the oxirane first. We're going to protonate the epoxy first. When we protonate the epoxy first, part of the charge is going to be on the most stable cation, where the most stable carbocation would form. That makes it now more susceptible to attack by weaker bases, weaker nucleophiles. Okay, so if we have a weak nucleophile in a acidic solution, we're actually going to have the alcohol on the least substituted side. Okay, so knowing what you have in your system, if it's strong nucleophile with the water at the end, you're going to get the least substituted system. If we're doing an acid with a weak nucleophile, we're going to end up with the least substituted alcohol. Okay, so this is a nice selective reaction, and so you have to look at the reagents to see which side is going to open and which way it's going to open. Okay. Yeah, and all of these, because it's symmetrical, we really can't tell which side it attacked. But when you have it substituted, you can. All right, I'm going to stop here and we're going to continue on with this and ethers for our next lecture. And look for an email about the reaction tables. I just need to draw out a few structures and then I'll show you what I want for that, okay? And then it won't be, will still count as a group project. It's just we need to finish up the ethers lecture on our next class, which will be on Tuesday of next week. All right, question. Oh, let me stop recording and you can stay behind and ask questions if you want or head off to your next class.